Lewis structures. So valence electrons in the main group is equal to the group number if we're doing the A and B. So if it's in the 1A, if you guys remember, do you guys remember electron configurations? So everything in the 1A has an S1, like hydrogen's 1s1, lithium's ends with 2s1, sodium ends with 3s1. So they have 1 equals 1 valence electron, right? If I'm in the 3A, then I have an S2P1 configuration, which is 3 valence. If I'm in the 8A, I should say except helium, then I would have, helium is S2. But besides helium, they're all S2P6 with 8 valence electrons, right? These are the noble gases, yeah? So let me actually, I want to make a chart here. So 1A, 2A, 3A, 4A, 5A, 6A, 7A. I'm going to skip the transition metals and the inner transition. 8A, 7A, 8A. If this holds true, then each electron is a dot. So hydrogen would have 1 dot, and beryllium would get 2 dots, and boron would get 3 dots, and carbon would get 4 dots, and nitrogen would get 5 dots. So usually I put them in singly, up, down, right, left, and then as a single atom, and then I start to pair them. So I'm going to pair the top. You could pair wherever, it doesn't matter. Then oxygen, let's have pair, pair, single, single. And then, let's see, 7A, it would be fluorine, pair, 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 single. And then finally, neon, which is the first 8A that's not helium, would be pair, 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 pair. So this is the number of electrons. Let's find the number of bonds, right? So to make a bond, you need to have an electron to share usually. So how many bonds can hydrogen make? 1, right? If I only have 1 electron, I can only share that 1 electron. I can only make 1 bond, yeah? For hydrogen, that's okay. What about beryllium?
2?
Yeah, 2 bonds. And so typically, and then the number of electrons after sharing. So now hydrogen was sharing 1 and making a bond. So let's do that. So hydrogen has an electron and another hydrogen has an electron. Let me go back here for a sec. And then they make a bond. And so now they each have 2 electrons, right, by sharing. So hydrogen has 2 electrons now after sharing. And that's cool for hydrogen because it actually only wants to get to S2. In the first energy level, if you remember hydrogen's electron configuration is 1s1, right? So it only wants to, there's no p orbital block in the first energy level. So hydrogen actually has a full allotment of electrons. But what about beryllium? If we get 2 bonds, how many total electrons would we have?
3.
Well, no. So each.
Oh.
So
4.
4, right? Because I'm at beryllium. Let's draw a diagram. So beryllium is going to have 2 electrons, and then it's going to share. Let's say it's sharing with hydrogen, for instance, and it shares with hydrogen, and now the beryllium's counted as having 4 by sharing, right? So beryllium's actually what they call electron deficient. It can never get to most atoms want an octet. They want to have 8. Hydrogen's weird. It doesn't need 8. It's actually quite stable with 2. But beryllium wants 8. It can't get it. What about boron? How many bonds?
3.
3. Good. And if it gets 3 bonds, how many electrons total will it have with sharing? Following this pattern.
6.
6, good. Okay, so boron's also electron deficient. It wants to have 8, right? So in general, there's an octet rule. Let me just put that. Octet usually means getting 8 electrons, which approximates having an S2P6, which would approximate a noble gas, which is very stable. Okay. What about carbon? How many bonds will carbon make?
4.
8.
Okay, so someone said 4 bonds, and I think the 8 was for the number of electrons in those bonds, right?
Yeah.
Yeah, okay, good. All right, so what about, nitrogen? Now this is interesting. So if 4 bonds gets me 8 electrons, does nitrogen want to have 4 bonds? How many bonds does nitrogen want to have?
3, no?
3.
Good. So if nitrogen has 3 bonds, then how many electrons? If I'm going to basically add 3 electrons to it, so it would get 8, right? Yeah.
Yeah.
So we could put a little star here for Chem 1A. Some atoms can have more than 8 electrons. So not nitrogen, but on the periodic table, if I look below nitrogen, like phosphorus, arsenic, they can actually have more than 3 bonds. They can have more than 8 electrons. But I put a star there just so you guys know. So there's more to this story, essentially. 6A. How many bonds does oxygen need to get 8? Following the same pattern.
2.
2, good. And it gets 8. So again, not oxygen, but atoms below oxygen like sulfur can have more. Fluorine. How many bonds does fluorine want to get 8? It already has 7.
1.
Just 1. Good. And it gets 8. Now, again, atoms below fluorine can sometimes have more bonds. Okay, so what about neon? Neon has 8 electrons already. So how many bonds will neon make?
0.
0. It already has 8. And again, some atoms below neon can actually have more than 8. So I want to talk about some good ideas for Lewis structures. And then we'll go through some steps for doing Lewis structures. So good ideas is you should pair unbonded electrons. So I'll see some people will do stuff like they have a nitrogen, and then let's say it's a carbon, and then maybe let's say there's 2 more bonds over here to something else. How about oxygen, something like that. And then they'll have an electron here and an electron there. And you want to have them paired, right? They imagine that they're in a p orbital. Oops, p orbital. So that I wouldn't do this, but rather I would do something like the nitrogen would put them together, basically. Yeah. Well, let's continue. So pair unbonded electrons is really important. This one, biology teachers violate this, but I show bonds with sticks, right? So I like to see that. So some people, like for water, they'll say, oh, there's an electron pair between the oxygen and the hydrogen, and so I don't know who's bonded to what. If I'm, if this pair's here, I'd rather see it, show it as a bond, right? So that's kind of a nice thing to do. This is kind of a hard and fast rule. You can have a maximum, as far as I know, a maximum of 3 bonds between any 2 atoms, right? So X to Y, I can have a single bond, or a double bond, or even what we call a triple bond, but there is no such thing as a quadruple or quintuple bond, right? I should make it plural. There we go, 3 bonds between any 2 atoms. All right, another really good rule is, and I'm gonna put usually, because there's some Chem 1A stuff that you can violate octets, but usually you have a maximum of 4 bonds on any atom, right? So if this is the bonded atom, it can have a bond to 4 different things, or it could have a triple bond and a single bond or whatever, right? So this isn't violate. See, I have a bond over there. I'm not violating the rule because rule number 3, I have 3 bonds between X and Y, but then X and Z, I can have a 4th bond. Usually maximum of 4.
Just to clarify this, with the sticks, 2 sticks just means like 2 electrons, right?
No. So one stick is 2 electrons.
Okay.
2
So-
sticks is 4 and 3 is 6.
Yes, that's correct. 1 stick is 2. Let's go back here for a sec. So we had hydrogen, single electron, 1 stick, 2 electrons. Yeah?
Yeah.
Okay, good. So sticks are 2, dots are 1. Yeah? Okay, good. Perfect. You know, usually you want to achieve octet. Usually octet. Let's have a couple other good ideas. I'm going to go down the row here. So 6, no rings. We'll do rings unless you have 3 or more carbons. And usually 5 to 6 carbons is the sweet spot for rings happening. So pair unbonded electrons show bonds with sticks, maximum of 3 between 2 atoms, maximum of 4 on a single atom. Usually get an octet, no rings. If you have to add extra electrons, you do it to the outside. And you remove electrons when you have a positive charge. And you remove electrons usually from the inside of the structure. Another good idea is you're usually a center atom with others outside. So the basic game is I'm going to have an atom in the center, and then I'm going to have other things attached to it. Okay, let's give it a lone pair, whatever, something like that. And then the last thing, that's a lot of ideas, isn't it? Last thing is use a pencil. Because you're going to erase it constantly. So pair electrons, show bonds with sticks, 3 bonds between any 2, 4 bonds on any single atom, usually an octet on each atom. No rings unless you got lots of carbons. Add extra electrons if you have a negative charge to the outside of the structure, so like out here. Remove electrons from the inside, from in here. Usually center atom, others on the outside, use pencil. Okay, good ideas. Now let's show how to do Lewis structures with the steps. And my example is going to be water, H2O, first. And then we'll all do several examples. Water better not be in my set here, right? Good. Okay, we'll do water. Perfect. All right, so the first step is put the atom with the most bonds in the center. And I'm going to have a caveat for this rule. If they're the same, or the same number, not the same atom, then if they're the same, if they make the same number of bonds, then you choose the one that is lower or left on the periodic table. Okay. Who will go in the center? Who makes more bonds?
Oxygen.
Yeah, oxygen makes 2 bonds. So if hydrogen only makes 1 bond, it makes no sense to make it the central atom, right? Does that make sense? Okay, so far so good. Okay, so that's the only time we need that, is when I have to think about bonds. Let's continue. This step sounds kind of pedantic, and I'll see why you think it might be pedantic. Put in valence electrons. And make, quote, obvious bonds. So I think, so someone might say, that's absurd. What do you mean by obvious? Why is it obvious, Mr. Canton? Well, so let's put in the valence electrons first. And I actually think this is a really important step. Some people start making bonds right away, but maybe I should actually break this into 2 steps. There's step A, which is put in valence electrons, right? And then B, well, you make a couple bonds right off the bat, right? I should make that plural. Or maybe you only do 1 bond. I don't know. Okay. But anyway, so valence electrons. So hydrogen has 1. So hydrogen's in the 1A. It has 1. Oxygen's in the 6A, so it has 6. And up there's 2 hydrogens. So each hydrogen has 1. Oxygen has 6. And so what I'll do with the oxygen is I'll put single electrons facing the atoms I intend to bond with. Now, at this stage, I have 3 separate atoms floating around. So no matter what the structure is, I'm going to have at least 1 bond from any outside atom to any inside atom. Does that make sense? Otherwise, I have 3 separate atoms. So why is it obvious? Because if I don't make a bond here and here, I have 3 atoms floating around. Does that make sense? So that's why I call it obvious, that you have to have a single unit at the end of the day. All right, so step 3 is actually a key step. So I put a star on it. For step 3, you want to check octets. And that usually means 8 electrons. There are some exceptions to this. So hydrogen only needs 2 electrons. And beryllium, like we pointed out, can only get to 4 electrons unless someone magically gives him electrons or whatever. And I'm sorry, beryllium 4 and boron 6 electrons. So there's some caveats. These are what I call electron deficient. And you can have expanded octets, which is more than 8 electrons, with a 3rd period or lower central atom. And so this rule, let me put it in brackets, because this rule is not going to apply to anything we're going to do today. That rule is for Chem 1A. Okay, expanded octets, I'm going to just skip it. But I just wanted to put it in there that whatever there's a way to check, there's a way to do expanded octets. There's another set of rules for these that I'm not going to cover. So here's what we do. So now we're going to look at each atom. So now this hydrogen's counted as having how many electrons? Now that it's sharing, I'm going to say now that it's sharing, it has 2 electrons, which is what it wanted. And this hydrogen over here also has 2. What about the oxygen?
It has
Yeah, it has 8.
So
4
oxygen
or 8.
Oxygen has 8 by sharing. It's sharing 2 with that one and 2 with that one. So that's 4. And then it has 4 by itself, 8 shared. And hydrogens have 2 each shared. That's a key rule. So we're happy. We actually, hydrogen is a special case, but that's hydrogen. You're going to see hydrogen all day long, even though it's a special case.
Wait, so why is it special?
Because it only needs 2 electrons. So most atoms want 8. But
Oh, okay.
hydrogen,
That makes sense.
beryllium, and boron are electron deficient. Okay, next step is check total valence electrons. And there's a caveat for total valence. If you have a negative charge, you add electrons. And if you have a positive charge, what are you going to do? You're going to remove electrons. Okay, does water have a charge? Do I see any charges anywhere?
No.
So I can't add any or take any electrons away from this structure. Let's actually check the total valence electrons. So oxygen, how many electrons before? Now it has 8 now with sharing, but how many electrons did oxygen have before? How many did it come with?
6.
Yeah, oxygen is element number 8. Technically, it has a total of 8 electrons, but 6 are valence. These are the outer electrons. These are the electrons that want to bond or whatever. There's 2 inside that we're ignoring. So oxygen has 6. Let's go here. And then hydrogen. How many there's 2 hydrogens. How many does each hydrogen have? Valence electrons before it bonded. How many electrons does hydrogen come from in nature?
1, right?
Yeah.
1.
Yeah, so I should have a total of 8 electrons in this structure. And that it just the valence electrons doesn't have to be 8. It's just by accident with water that it happens to be the same as the octet number. But how many total valence electrons do I see in this structure? I see 2 in this bond and 2 in that bond and 4 alone. There's 8. So if both of these rules are simultaneously correct, this is probably the best structure I can get. I'm going to do some other ones, but I want to mention the other rules. These other rules aren't really going to apply to water. So the next rule is you repeat steps 2 to 4 if necessary. So if I don't have my octet satisfied, or if I don't have the correct number of total valence electrons, it needs to be adjusted somehow. Does that make sense? So water satisfied both of step 3 and 4. I don't have to do it. Usually by repeating these steps, it means I'm going to make some more bonds, and then I'm going to recheck the octets and recheck the total valence. That's what repeat 2, 3, 4 means. Another rule that doesn't apply: if an ion bracket and declare the charge. And we'll do an example of that too. If it doesn't have a charge, I better not put a bracket around it. I'm only going to put a bracket around a Lewis structure that has a charge. For 7, I say, Pete, double check while you're learning, okay? This is kind of an extra, just double check your octets before you write your test answer, what have you, okay?